Hi, this is Pete, and on audio, sorry, without video, I have JJ in tow. JJ is one of the DevRels here at Deephaven, who's also a very competent data scientist and into machine learning and AI. So he and I are going to walk through um, a use case sort of at the other extreme from the simple table operations that I showed you before that uses Python and AI in real time to do a simulation of tracking credit card fraud, something that JJ's worked on before and tried to emulate here with a simple program. So we're going to first get rid of my face and then first make sure that JJ's still here with us. JJ, you there?
I'm still here.
Okay, sorry to not put you on video. I promise you, everybody, JJ is a better looking guy than what just showed up on your video there. So the first that we're going to actually run an application that JJ wrote. I'm going to try and run it and ask questions as we go. All I'm doing is I'm using a Docker image that he created that's out there in the Deephaven examples repo, and we're gonna talk through the application and what it does. In the end, it's trying to receive credit card information in real time and to help determine if there's potential fraudulent activity. So JJ, can you just describe, this all comes from a Kaggle data set and an exercise that's been described here. Yes, can you give a quick one on that?
Yeah. I actually, so this project actually initially stemmed from some work I did in grad school, doing some data science work. All of it was post-processing, including the original project that I did on this. But this data set has 48 hours of anonymized and PCA transformed credit card purchase data for European cardholders. All in all, there are 284,807 purchases across 48 hours of time. And approximately, I believe it's 0.27 or 0.027% of those are fraudulent. So what we're dealing with here is an anomaly detection problem.
Okay, great. So I think that application looks like it's running. As you know, when you run a Deephaven application, there's lots of ways to hook up clients to that local server that I'm now running. But one of the ways that I really like, and is a great way for just exploring data and looking at things in real time, or is via this web front end. So when I launch this web front end, it comes because I used the image that JJ had prepared. It comes with these notebooks that he had that he'd seeded it with. So what we're going to do is we're going to run these notebooks one by one, JJ, and maybe I think you can see them, and maybe you can help us talk things through. So the first step is this data preparation, right? So so what you're doing is setting up the data to be friendly to this SciKit-Learn model for DBScan. Yes.
Exactly. Yeah, DBScan is a clustering algorithm that is robust to noise and a wide variety of applications, including this credit card fraud purchase problem. So there are two parameters that are required to pass into Scikit-Learn's DBScan. The first is what they call EPS or epsilon, which is the neighbor distance that it will use to calculate neighbors within a neighborhood. And the second is a min samples. Basically, if at least min samples other data points exist within the epsilon radius of 1 point, it will be considered part of a cluster. And then there's some additional math and operations used to separate one cluster from another. But in this case, for this problem, we are only looking for one cluster. So none of the other optional parameters are that important.
Perfect. And this model is described more here. There's a link to it that also goes into it here. It's beyond the scope of this short little video to talk about through all of the capabilities of this clustering model. Okay, but we've run this program, right, that you talked about, which is getting that CSV data from Kaggle as you described, and then I think you're doing a couple of things here, right? You're splitting it out into fitting and testing data, so training and testing data, right? And then you're also doing some things, I think, to support your choices for those parameters. So as I understand it, there's 28 or so dimensions of data. You've isolated 3 that have anomalous looking profiles because those are the ones to focus on. Is that right?
Yeah. So as you just mentioned, there's 28 anonymized credit card purchases, and what we want are the purchase metrics of any subset of the 28 in which the fraudulent and the valid purchases are most dissimilar from one another. And
Yep.
based on some manual inspection, I decided on V4, V12, and V14.
Yep. And you said 28 purchases. You meant 28 like dimensions of the data.
Yeah.
Okay.
28 purchase
That's fine.
metrics.
Yeah,
28
cool.
dimensions.
And then so we're going to focus on these three in the model, and then you've got something here that describes an elbow, as I understand it, which is a good choice for that other parameter, right? Can you go into that just a bit more?
Sure. So as I mentioned previously, dbScan expects two arguments. The first is a neighbor distance, and the traditional way to choose that is to plot the nearest neighbor distance of every point in the set in ascending order. And so that's what we have here. We actually, there's 30 some odd thousand in this 4-hour window that I'm using. So you can see the x-axis starts at about 30,000. I plot the last subset, and then you can manually choose approximately where the elbow is, and that just happens to be right around a neighbor distance of 1. So I chose 1 for the neighbor distance for this application.
Nice. And the fact that it's 1, we don't have to read too much into that, right?
Yeah. And then the second argument is the number of neighbors within a neighborhood. The general rule of thumb is you want more neighbors than the number of dimensions you're using. In this case, I'm using 3, and I played around with some different values and found good results with 10 neighbors. So.
Very good. So the second thing we want to do is train this model given the parameters you just spoke of, right?
Yes.
So that's this. Can you just talk us through what we need to learn here?
Sure. So when I initially did this back in grad school, I did it all in Python using pandas data frames. In this case, we actually use Deephaven tables, which will really come in handy for the next script, which does the real-time stuff. But here, what we do is, what's great about SciKit-Learn is that its API is extremely simple and accessible. So after importing the required statements and doing the data preparation, all we have to do is fit the model to our data. So I select the subset of columns. I then apply that, dbScan, perform dbScan function, which simply creates a dbScan model and fits it to the data in the Deephaven table, which has been transferred to a NumPy ND array using Deephaven Learn.
Perfect. Yeah. So you hit on the thing that I was hoping you would hit on. There is a translation layer here that is being performed between this, in this case, static table. And Deephaven, right? So we use a gather compute scatter model here that we call Deephaven Learn that we've documented, right? And essentially this is, in simplest terms, this is a way of delivering data, into NumPy arrays and tensors so that these these libraries have the objects that they want to work with, right? And in this case,
Yes.
We're looking at static data, but we'll show in a moment how this, the Deephaven Learn library also magically works for real-time data as well. Is that correct?
Yeah, exactly.
Okay. So I don't know if I actually ran this thing. Let's see. Did I? I probably did.
I don't think you ran the train model script just yet.
See, we were supposed to run it while we were talking, so there we go.
That's okay. This only takes a few seconds. But as far as Deephaven Learn goes, it's really nice because you just define a couple of helper functions which define how the data is transferred to and from Deephaven tables and the Python object of your choice. You can select subsets of rows and columns, and you get the added benefit of Deephaven's incremental table update model, which does most of the heavy lifting for you, especially when it comes to real-time data, as we'll see in the final script.
Okay, fantastic. Here we go. It looks like the best thing to look at here is which table?
That would be there is
valid
clustered, I think.
So there's the
5
cluster
tables that get created.
Right. So here's the different dimensions that you spoke of. I assume the size of the purchase and whether whether it was actually a fraudulent purchase or not, and we can see of the fraudulent purchases how many ones were predicted to be fraudulent from your model, right?
Yeah.
Okay.
Yes.
Perfect. So it's beyond. I don't think we want to delve into how to improve this model or whether this is. We know that this is good. We don't want to spend too much time on determining how to make it better. I think what we want to move to pretty quickly is how to deliver this then on real time, right? So I'm guessing what you've done here is you've set up a replayer now on that
Yep.
test data, and you've taken that second group, the out of sample data, and are pushing it through as if it's being inherited by this model in real time. Is that right? And then you're
Yes.
delivering, I assume, the same type of output, a determination of is this fraud or not, based on the scikit-learn clustering algorithm in real time, with the Deephaven Learn model facilitating the bridge essentially between the Python and the query engine in the back.
Exactly.
Okay. So now we'll run that, and I assume the table we're going to care about here is predicted fraud live.
Yes.
Okay, so we could go to.
So there's once again, it creates one additional table, and then there's 4 derivative tables from that, so that I can keep track, or anybody that uses it can keep track of where the model is doing things correctly and where it's not.
Right. So let's just pull in time, which is just to see that this thing is actually ticking.
You missed an I.
Oh, yep, time actually has the word time. There you go. Thanks. Okay. So now I think we can see that this is coming in real time because that replayer is playing it in accordingly, right? These are different events, and it's characterizing them in the predict, it's using this to predict whether it is fraudulent or not. Obviously, we have a statement for these things as to whether it is or is not fraudulent. And again, I guess we could filter this if we wanted to and say which ones are predicted. There's 2 predictions that were, false positives, and oh look, lo and behold, the only one that's come in so far that is, is fraudulent. We were effective at predicting that. So nice one. You're 1 for 1 on this one, JJ. So we could, you could see that new data is coming in. This has only been a small number so far, 191. There's gonna be tens of thousands that play in here over the next couple of hours, you say, right? And the combination of the Deephaven engine, the Learn library, and Scikit-Learn's DB scan are gonna produce the goods to predict whether something's fraudulent.
Yep. And we could see that too, that the scripts that were actually run really weren't that long. The code is not overly complex. You get all the benefits of Deephaven without having to do a ton of extra work to take full advantage of them.
Yeah, I think one of the salient selling points for our customers and users of Deephaven is this idea of migrating from static to real time is straightforward, or moving from training to production is oftentimes just a flip of a change of a few parameters and a flip of a switch, as described. So very exciting stuff, and thanks for talking it through with us, JJ.
Yeah, sure thing.
All right, take care now.